Okay. Well, thank you all for joining. We're really excited to be able to do this first webinar in a webinar series that we're going to be putting on centered around precision fermentation in the circular bioeconomy. This series is co-hosted by the Levenick Center for a Climate Smart Circular Bioeconomy. That's the center that I'm a part of. And then also the Illinois Fermentation Agriculture Biomanufacturing Tech Hub, or IFAB, and the Integrated Bioprocessing Research Laboratory, or IBRL. Just some housekeeping things from the start. This webinar is being recorded, so we will have recordings put up online later on. And in future correspondence, we'll also be providing a link for the previous webinars that you'll be able to then see online. If you have any questions throughout, feel free to put them in the chat. And when we have a little bit of time at the end, we can address some of those questions. And we're hoping for this webinar to last anywhere from 30 to 40 minutes. We don't intend to take up the full hour, but we'll see kind of depending on where the questions and discussion goes. So the format of these webinars going forward, it's really going to be kind of three pieces. So the first part is we're going to be providing a sort of framing for the webinar around where we're talking about or where we're at in the circular bioeconomy. And then we'll have someone from the university who will be speaking then about the specific topic, likely someone from IFAB or IBRL. And then we're ideally going to have also an industry perspective at the end of each of these webinars in order to kind of ground truth it in real life based on what we talked about. So first off, I'm going to start this session by talking a little bit about the Levenick Center, just because it's a very new center on campus. We've only been around for about less than a year right now. And so to just give you kind of an idea as to what our goals are on campus, my name is Ken Ruffatto. I'm a research scientist, primarily working half with the Center for Advanced Bioenergy and Bioproducts Innovation, but also as the project manager for the Levenick Center. Our director is Dr. Jeremy Guest. He is a Levenick professor and also a professor in civil and environmental engineering. The Levenick Center is housed under the Institute of Sustainability, Energy, and Environment at the university, and it was started by a very generous donation from Stu and Nancy Levenick. And so just to give you an idea as to what, some of our goals are as a center, we primarily work with faculty. However, we're always open to talking to industry and seeing if there's ways that we can collaborate, industry or government. So we work to integrate faculty across campus that are working within this bioeconomy context. And the idea is to create more of an interdisciplinary network and a shared vision for the bioeconomy. Since a lot of people work in kind of individual spaces, we want to show kind of the larger, broader systems level impacts that they have individually. And then we also then work to try to strategize around cohesive initiatives, around strengths that we have at the university. And the reason for this is it allows us to better coordinate opportunities for things like research or for funding proposals or policy leadership. And our main initiatives that we're focusing on for this year are, and likely going into next year too, are AI for the bioeconomy. We did a workshop with a bunch of faculty back in November. And then miscanthus to bioproducts. So we're looking at how miscanthus is used as a feedstock in order to produce multiple types of bioproducts. Phosphorus in the bioeconomy, and then lastly, precision fermentation, which is the main subject of this webinar series. And so part of that too is we're looking to create demonstrations through regional models. We have a postdoc that works with us, Dharmendra Singh, who's on the webinar right now. But he's working on creating right now a regional model for miscanthus, looking at how using miscanthus as a feedstock, what sort of circularity pathways there are throughout the bioeconomy on a county level, state level, and a regional level. To try to show kind of the real world examples of how the work done at the university can be done in practice. So first framework, though, that we need to get our heads around is what exactly is a circular bioeconomy. So this is our very kind of simplified example of what a circular bioeconomy looks like. So we see it as sort of two parts. One part is the bioeconomy, which is already exists and is relatively robust, especially in the Midwest. We have crop systems, which can go anywhere from the micro scale to the macro scale. We have researchers working on the plant genomics part of it, all the way up to looking at satellites and field level and regional level data. And then those feedstocks go into the biomanufacturing process. And that also is at a small level from enzyme and protein engineering or metabolic engineering, all the way up to looking at actual siting of full biorefineries across the nation. And then we have the bioproducts that go then into our marketplace. And this is looking at the economics of the market. And so this is our main bioeconomy. And then each of these components have certain waste products that come out of them. And so we have another component, which is the circularity part, which is resource recovery, where we're trying to recover as many valuable resources from those waste streams as we can and recirculating them back to the different parts of the bioeconomy as best we can. So we're looking at really to reduce, reuse, and recycle as much as we can. And then overarching this whole system is the human environment systems. And this is really where kind of human behavior comes into each of these different components. And this also encompasses more of the policy landscape then across the whole circular bioeconomy. So again, this is kind of our simple way of looking at it. There's these five main themes, and this is really how we organize faculty when we're looking at the university across these different themes and look at how we can actually integrate them between all of them. So what we're looking at today and as part of this series is precision fermentation and how it fits in as a bioprocessing technique. And so what we hope to do then throughout this series is look at how the introduction and usage of precision fermentation can impact both the upstream and the downstream parts of the circular bioeconomy. So we organized all of our seminars around these various different components then. So these first two seminars are talking more about the actual process of precision fermentation itself. So you'll get an introduction today. And then in May, we'll be looking at scale up of precision fermentation processes. And then in June, we'll be looking at the marketplace component and how products generated through precision fermentation could help redefine the marketplace. And then in September, looking at the policy implications and type of policies we want to look at as part of these products and things we need to consider on a policy front. And then we have the crop systems, which is looking at how crops may change or the types of crops we use may change based on the introduction and usage of precision fermentation. And then there's potentially a seminar, sort of a bonus seminar at the end. We'll see if we can get it together surrounding sustainability and precision fermentation systems. And this would be looking at sort of reuse pathways and such, depending on the type of expertise. We'll be doing that seminar depending on the expertise we can gather on campus. So with that said, we're going to be going into our first seminar, which is looking at an introduction to precision fermentation. We are very excited to have Dr. Vijay Singh to give this presentation for us. He is a professor in agricultural and biological engineering, and he is also executive director for IBRL. So I'm going to stop sharing, and then Vijay, you can start sharing.
Okay. All right. Can you see my slides? Is it in the presentation mode?
Swap them.
Okay.
No, I can see the next slide on the right side. You may want, yes, swap.
Yep. All right. How about now?
Yes.
Yes.
Okay, very good. Well, good afternoon, everyone. As Ken said, my name is Vijay Singh, and it's my pleasure to provide this introductory talk on precision fermentation as a part of Levenick Center, IBRL, and IFAB seminar series. So when we say precision fermentation, it sounds very futuristic and scientific. However, all we are doing is just leveraging a natural biological process that humans have been using for thousands of years. We have been consuming fermented products like yogurt, cheese, beer, kimchi, and wine for a very long time. Even with easy to visualize end products in mind, since we don't see fermentation with our naked eye, it can be hard to visualize. So what is it? A good example that we can use is bread baking. Yeast and bacteria are breaking down the carbohydrate sugars in the flour to produce flavor compounds like sourdough tang, carbon dioxide that forms the bubbles to make the bread rise. So that is, in very simple terms, what precision fermentation is, or fermentation is. Here's how we do precision fermentation. Basically, it is a tool for biomanufacturing different products that include food, fuel, and consumer products. So we start with feedstocks. These can be a variety of feedstocks, sugar crops, cellulosic crops, waste products. All we are doing is recovering the carbon and feeding that carbon to an engineered microorganism that has been programmed to produce a very specific metabolite. We do that in the fermentation tank, followed by what we call downstream processing to recover that product. Now, that product by itself or in combination with some kind of chemical catalysis can be used to produce all kinds of different consumer products. And that is what we are trying to do with this precision fermentation process. Now, there are three main categories of fermentation. First one is traditional fermentation. Traditional fermentation is a process of changing food through microbial anaerobic digestion. This is how we make yogurt, bread, cheese, tempeh, alcohol, and many other products. Biomass fermentation and precision fermentation have nearly identical processes, but one main distinguishing factor. In biomass fermentation, the microbe is the product. Whereas in precision fermentation, we use microorganisms to produce specific functional ingredients. These microorganisms are programmed to be little production facilities, and it enables us to efficiently make specific proteins, enzymes, flavor molecules, pigments, vitamins, and fats. Here are some very common microorganisms that are used in precision fermentation. So Saccharomyces cerevisiae, E. coli, Pichia, filamentous fungi, all these microorganisms can be used to produce all kinds of different products. Now, all this precision fermentation is primarily driven by precision biology. And what has happened recently is that the cost of precision biology has significantly dropped. So new information technologies like machine learning with deep neural networks are allowing us to analyze very complex biological processes with far greater speed and accuracy than ever before, and to manipulate the genetic matter to design specific organisms that can be programmed to produce molecules with very precise attributes has become very easier. Back in 2000s, it used to cost millions of dollars to sequence genome. Today, that price has dropped to less than $1,000. And it has become very, very fast to do this. And as these innovations happen in precision fermentation, the cost of precision fermentation is dropping down. And we have already disrupted markets in pharma, cosmetics, and biomaterials. And it's expected that very soon we'll achieve price parity in food products. And that's when a lot of disruption is going to happen for conventional industries. So, how is all this happening? What's happening is that the researchers or companies are using this design, build, test, learn loop to engineer different microorganisms to produce very, very specific products. And this whole development cycle of design, build, test, learn has uh, uh, become very, very fast. So, what's happening is in a very short period of time, a researcher, a company can bring these microorganisms and then try to do scale up in order to produce that functional product. And this is what's driving this growth in this whole precision fermentation in bioeconomy. If we look at bioeconomy, it was estimated back in 2022 that in US, it was close to about $1 trillion. And it was estimated that this number is expected to go to close to about $4 trillion in a very short period of time. And it's all because of that precision biology, the advances, the innovations that have been made in precision biology. And a very big component of this bioeconomy is precision fermentation, which is also increasing rapidly. In 2023, that was $2.8 billion. And it's expected by 2030, it might achieve close to about $40 billion. Other estimates put that by 2040, this number might actually go to close to about $200 billion. So a huge amount of growth in precision fermentation and overall bioeconomy. But what is driving all this growth in precision fermentation? Well, there are several factors that are driving this growth. The first one is sustainability. Sustainability has become a mega trend, which is creating a market pull. Producers are seeing increasing consumer demands for bio-based alternatives in some specific areas. And most of them are premium items like fashion or automotive, where the costs are much higher and barriers to purchase are kind of less barriers. Volumes are low, and then these companies are looking for brand recognition. Food security is another reason for this precision fermentation, growth in precision fermentation. Precision fermentation gives us an ability to produce food without conventional agriculture. This has become very important in some countries around the world where there is no suitable arable land to grow food. And precision fermentation is the only viable option to do it. Affordable feedstocks and multiple affordable feedstocks. The cost of feedstock makes about 60 to 70% of the total production cost for bio-based materials. So a reliable access to available, affordable feedstocks of good quality and consistency is vital to maintain the cost competitiveness compared to conventional petroleum-based alternatives. Technological innovation. Again, advances in synthetic biology and metabolic engineering has allowed us to develop these host microorganisms that can produce very pure, high concentrations of metabolic products. And as I said earlier, that these metabolic products by themselves or in combination with chemical catalysis can be used to replace petrochemicals, and might even give better functionality that we cannot even get from petrochemicals. And there are several examples of that. And finally, there is a highly positive and supportive regulatory environment. Regulations that aim to increase demand, either banning single-use plastics or putting tax on use of fossil-based materials, is all driving this growth in precision fermentation. Next, what I'm going to do is give you example of 6 different industries where precision fermentation is playing a very significant role and disrupting a lot of conventional markets. So the first one is in biopolymers. There are all kinds of different polymers being produced: protein biopolymers, cellulose, starch, polylactic, other polymers, with all kinds of different applications in medicine, packaging, agriculture, manufacture, and water management. There was a report that came recently where they looked at 532 startups and emerging companies that are producing biopolymers through some of and most of them through precision fermentation. Next one is the chemicals industry. The chemical industry worldwide is a $6 trillion industry, and about $450 billion of specialty chemicals and material markets or materials are made in this chemical industry. And it's estimated that close to about $130 billion worth of that $450 billion market can be done by using precision fermentation. So the growth is just enormous, that there's just enormous amount of potential for precision fermentation to play a role in production of these different chemicals. The next one is alternative proteins. And precision fermentation is expected to become a low-cost technology, generating huge opportunity in alternative protein space. This market, continues to grow, but also had several bumps. And many people don't take this seriously and point to usually to the stock market woes of some of the companies in this space. However, overall, this industry is expected to do very well and continue to grow, because in order to meet the protein demand of the growing population, we cannot ignore proteins produced by precision fermentation. So this is an area that is expected to grow as more population, as more affluence increases. People are going to demand more protein, and we cannot just intensify conventional animal agriculture to meet that growing demand. So precision fermentation is one of the alternatives to meet that demand. Another big area is in lipids. There are companies that are in the space that are producing very tailored lipids for very specific end use markets, whether it's for cosmetics or to bring the texture and the flavor profile in different meat products and things like that. So that is another big market that precision fermentation is playing a very critical role. Then comes the biomaterials. And this starts with textiles to polymers that are going into all kinds of consumer products, shoes, surfactants, pigments, leather, parkas, the one from the moon parka from North Face. All these can be made through precision fermentation. And not only just these consumer products, including concrete, can also be made by precision fermentation. So here on the top right panel is concrete in North Carolina that was made by precision fermentation. And the one below that is from Denmark for concrete that was also produced by precision fermentation. Okay, the last one is the cellular agriculture. Cellular agriculture is precision fermentation-based technology to produce milk, egg, meat, fur, leather, and other ag products traditionally produced by conventional agriculture and conducted by growing plants and animals. And conventional agriculture is challenged by depletion of arable land, increasing costs of water, fertilizer, environmental pollution, and it's making it challenging to meet the upward demands of the growing population. And compared to conventional agriculture, cellular agriculture requires 80% less land, 94% less water, and 76% less overall greenhouse gas emissions. And that is what is driving this whole cellular agriculture. As I said earlier, there are countries around the world that don't have any arable land, but they still need to meet the demand, growing demand for food, and precision fermentation is the only alternative they have to create that food. All right, now, in order to do this precision fermentation, you need very large quantities of carbon, okay? And there's no shortage of carbon in the United States. we have close to about 1.4 billion tons of corn that is produced, and this corn crop continues to grow year over year. So at the bottom, you can see that by innovations in corn development, we are seeing a higher and higher yield of corn being produced every year. So there's plenty of carbon that we can get from corn. But not only just corn, there is about 1.3 billion tons of cellulosic biomass that is available to us every year. This is the report from USDA and DOE, which they have, updated multiple times. There's a lot of carbon, cellulosic carbon, that is available, and there are many companies in this space trying to produce clean sugars or sugars from this cellulosic biomass. In addition to corn and cellulosic biomass, there are other waste streams that can also be used for making in precision fermentation and providing cheap carbon. One is carbon dioxide. We have a project right now as we speak with DERPA where we are trying to make food, complete food with macro micronutrients profile using air. There are companies that are in the space, and there are companies that are also using industrial waste streams and converting the carbon in those streams into high value precision fermentation products. Now, how does it actually work? So here are this fermenter. That's the main fermenter where most of the fermentation is done. You start with the microorganism. You then, develop it into seed cultures, then into a seed fermenter, and then you inoculate the main fermenter. And after doing that fermentation for a couple of days, maybe 3 days or about a week, you have the product, and then you do the DSP in order to recover that particular product. This is what a precision fermentation will look like. Inside, you'll have an agitator. You'll have several pumps to pump acid or base in order to maintain the pH. There'll be dissolved oxygen concentration that you have to maintain. You need steam, you need chilled water to cool these fermenters, steam in order to do the CIP or to heat up the fermenter. So this is what a typical fermenter would look like. And I think this is one of the fermenters here at IBRL. Now, this is all great, but there are some challenges also associated with precision fermentation. And the biggest challenge is related to scale up. Most of the microorganism development and testing is done at lab scale in very small micro titer plates, which are then subjected to capillary action, therefore do not represent scale-up performance that involves turbulence and heterogeneities. Sometimes these challenges, it makes it very challenging to predict the strain's performance in the bioreactors. And large-scale reactor studies are very resource intensive, limiting the number of process development studies that can be performed. So, typically in a large-scale fermenter, when we look at the productivity of the microorganism, a 20% difference in the productivity can throw off all your revenue and profitability. So scaling up is very, very critical in precision fermentation. And this is where IBRL is playing a very critical role. This is where, we work with a lot of companies trying to improve their fermentation processes and preparing them for demonstration scale or commercial scale precision fermentation. This is where also a lot of activities happening in the country, trying to develop demonstration scale capabilities. Obviously, IFAB is front and center in doing that, working with our industrial partners in Decatur, also expanding the footprint of IBRL. But there are other efforts that are going on by the federal agencies as well as private companies trying to develop demonstration scale and commercial scale capability in precision fermentation. I think that's all I have. Thank you very much. I can take some questions.
Great. Thank you, Vijay. Does anyone have any questions they'd like to ask? either use the chat or if you want to unmute.
Sure.
Guess I'll go first. This is John Eddington. I represent the Midwest with Eppendorf and formerly was a scientist at ADM for several years. I'm curious, are you seeing much of a shift in solid state fermentation starting to take hold?
So yes, there are some companies that are doing solid scale fermentation and that have also brought some commercial products into the marketplace. But most of it is submerged fermentation. Most of the work that we see or the activity that we are seeing is in submerged fermentation.
That's good to hear. I didn't waste half of my life.
Yeah.
Are there any other questions? Okay. If not, I mean, you always have the opportunity to feel free to send us an email if you have additional questions that we can answer. Um, that was our seminar today. Thank you again, Dr. Vijay Singh, for providing us an overview. You can see on the screen, these are the upcoming seminar or webinars that we'll be sending information about in the future. And once again, all these webinars will be recorded and we'll provide you access to those links later on. So thank you all for coming and hope you have a great rest of your day.
Thank you very much. It was a great presentation.
Thank
Thank
you.
you.